Anyway, it's a great pleasure to introduce Paolo Garbolino, who's going to, his title hasn't changed, so it's looking at Bayes nets for
No.
Is everything working okay?
No, to go upside, downside here,
Oh yeah,
upside.
have you got the clicker? You can use this.
Ah.
Use that. Hold on, we'll just put you on. Okay, so
Which?
just the button there. I think it's just that one there.
When you get to the computer.
Or that one there. Or that one there.
No.
Oh, okay, it's not working.
Once you get
Okay.
the computer.
So just that button.
Ah, okay. Okay. I can use
You
that.
okay with that? You sure?
Okay.
Okay, so pleasure to introduce Paolo Garbolino again.
You've done. Okay. It's okay. Thank you. Okay. Good afternoon, and I have to thank the directors of the program for inviting me. And I want to talk about not about Bayesian network for forensic scientific evidence, but about the network for evaluating human testimony. Because I think that we have some very good Bayes nets for evaluating scientific evidence when we have scientific laws, good mathematical models, and sometimes population statistics, which allow us to calculate likelihood ratios and Bayes factor. But what about when we don't deal with scientific evidence? In this case, assessing likelihood values, not to speak about prior probability, is a big problem, very hard problem, as we know. One of the biggest criticisms that can be made against Bayesian network. So my idea is to try to develop a model for a general model for human testimony that can be applied to several different situations, uniformly applied to different situations. And I make very clear the steps of my argument, all the assumptions I make to build the model, so you can fire on them and destroy them. This is what I expect from you today. My starting point is David Schum analysis of evidential reasoning. I agree that with Schum that evidential reasoning consists in building a chain of arguments from the hypothesis of interest to the evidence, a chain of argument in which each step is supported by some generalization or scientific law that provide a justification for that step. Because as a subjectivistic Bayesian, I think that yes, you don't the relationship, the arrows in a Bayes net that do not need to be causal relationship. I agree with Philip, and in my view, the relation is simply a relation of probabilistic relevance. But then you have to justify in some way why to say that there is a relation of probabilistic relevance between two variables. And usually this justification is based upon scientific law, or very often upon what we call common sense generalization. And very often that are a very tricky stuff, but very often we cannot avoid to use them. This is the only thing we have. So, this is a quotation from Joe Cadana and David Schum book. We assert a generalization. We are looking for some generalization and to ancillary evidence that together with the generalization, support our assessment of likelihoods. In the case of testimony, what are the relevant variables? Well, one is H, so the hypothesis that a certain event occurred, H of a proposition, you know, a linguistic item, and the evidence, according to my analysis, is the event that a witness says so and so. The evidence is not properly the content of the proposition of the witness, but the fact that the witness says so and so. Because this is an observed event. The other is linguistic item, an utterance of the witness. But the observed event is the fact that she says so and so. Observed event, unobserved event, H. So we have to look for a generalization linking the observed event that the witness says that H and the unobserved event, the hypothesis H. Now, again, I will use the analysis Schum makes of the human witnesses. He identifies three basic attributes: observational sensitive of accuracy, objectivity, veracity, and this is the generalization that David Schum put forward in his book. So, the ratio of the argument is that we have an observed event, a person saying something, and we have to answer to a why question, you know, in the terms of the philosopher of science, in the terminology of philosophers of science. The why question: why the person says that? He says that because he remembers that, because he's willing to be cooperative and saying what she remembers. She says that because she really knows that, and she remembers that. And I think that Schum's analysis tries to pick up these three basic steps in the answer to the why question. Why the person says that? Because it is accurate, it is objective, she's accurate, objective, and veracious. I know it's a very, very rough generalization, a common sense generalization, or we could also call it a law of folk psychology. So I take it as a first approximation. If you want, and if you are able to do that, we can make finer analysis of accuracy, objectivity, and veracity. Accuracy has to do with the psychophysical condition of the witness and also with the circumstances of the event. For example, it was a witness reporting an event which happened during the night with scarce light conditions. We can take account of it. Objectivity has to do with his cognitive capacity of the subject and, of course, his conditions, physical conditions, and veracity is, of course, with the willingness of the witness to tell the truth. So, if you want, we can give more finer analysis, if you are able, if we have scientific knowledge to do that. For example, we can, in the future, have some psychophysical laws about the physical condition, of the cognitive condition of the person. But I really think that this folk psychology law, as it is quite useful, and I don't think it will be easy to use other scientific generalization, because imagine we can really have a detailed list of psychophysical laws that, given certain conditions, can allow us to predict with certainty or with high probability the output. If the output, the answer of the witness. Though, will there be more useful of this generalization? Maybe it is a very, very long list of psychophysical law that at the end give more or less the same prediction that a folk psychology law. Or even if you are a materialist reductionist, you can think of physical law, of giving physical law governing the functioning of the brain and allowing us to predict exactly the output of the witness. Will be more useful of this folk psychology generalization? I don't know. Anyway, if we will be able to have such laws, we can use them instead of this common sense generalization. Then, how I use this common sense generalization, this folk psychology law? Well, I use an idea put forward many years ago by the philosopher of science Ronald Gere, and then applied by another philosopher, Peter Menzies, to the analysis of human agency. And this idea that has to do with how laws in science function is the following, given by this model. We have at the top a scientific law, our common sense generalization in this case, that is not scientific, of course, but we can put scientific law if we have them, or common sense generalization. Then we have a model of our system, a model in which the laws holds by definition, an ideal model in which the law holds by definition. In the model, the law is truth by definition. In this case, we have a model of an ideal person who satisfies by definition the generalization. Then we apply the ideal model to a real-world situation by making what Gere called theoretical hypotheses, which specify the relevant aspects under which the model is similar to intended real-world situation and the degree of similarity. Given that here we are at the Isaac Newton Institute, let me make briefly this example. This also, of course, for the laws of physics. I mean, in this analysis, we have, instead of G, put the Newtonian law of gravitation. For the idea that the model is a model of a real situation, for example, a two bodies model, Moon and Earth, and we say that in this ideal model of two bodies, the laws is true by definition. The laws of gravitation is true of definition. Then we apply the model to the real situation, Earth and Moon, making assumption. For example, we consider electromagnetic effects negligible, or we are interested only in calculated the orbit. If we want to do something else, if we wanted to apply the law for different reasons, the hypothesis could be different, and the ideal model is not valid in the real situation. For example, if our system of two bodies is Earth and a spaceship orbiting around the Earth, and you are interested in the radio signals between the spaceships and Earth, of course, the Newtonian model does not hold. We have to take account relativistic effect. So, in a sense, in this view, all models are literally false, are true only in idealized situation, but some of them are useful and can be used. So, Newton's law is literally false. We know that, because we know today that is a particular case of a more general gravitation law, but it has been useful, and it is useful today, because we can use it for many calculations today as well. So, I applied this model to my modest situation. We have an ideal model of witness satisfying that generalization, and then we apply the model to our real witness, making theoretical assumption. What are these theoretical assumptions in our case? Theoretical hypotheses. Well, of course they are that the witness is an accurate person, is an objective person, is a veracious person. It is true, the assumption is that it is true that the real person is accurate, is objective, is veracious. So the ideal model fits well with the real situation. And in this case, ancillary evidence that Schum and Cadane spoke about is the evidence that bears upon the truth of this theoretical hypothesis. The evidence we have to believe that the person is accurate, objective, and veracious. And our subjective probability for this hypothesis measures the degree of similarity of the real person with the model. How probable that the person is accurate, objective, veracious. Then, Schum's generalization can be split in 3 steps, in three hypotheses. If X is accurate person, then her sense give evidence of what she is, and so on, as you can see there. Then, assumption. Assume that the credibility attributes are independent properties. This is a quite arguable assumption, but let's assume that they are independent, because accuracy depends on the circumstances of the event, as I said before, if it happened during the night or by daylight, and the position of the witness, and so on, is opportunity to know really what was going on. Objectivity, and it depends on the functioning of his perceptive system. Objectivity depends on the functioning of his memory, of her cognitive system. And veracity can be considered independent from objectivity and accuracy. I know that the more difficult hypothesis is assuming independence between accuracy and objectivity. This is highly arguable, but let's assume it for the sake of simplicity and see what happens. So, given this, assuming that the credibility attributes are independent, we can build this directed acyclic graph when if the witness's senses gave really evidence of H, depend if the event H occurred, and if on the accuracy condition of the witness, external circumstances can be put in the node accuracy of accuracy, but if you want, you can add another node describing, pointing to S, and describing only the external circumstances of event H. Then, given the hypothesis, if the witness really believes H depends on whether her senses gave evidence of H and on the fact that it's objective or not. And if the event that the witness says that H depends on the fact that she really believes H and on her veracity. The node veracity can be a node with 3 values as a first approximation. Again, this is a very rough approximation, but let's use it as a first step. The 3 values of the node veracity is the witness is disinterested, the witness is interested in asserting H, the witness is interested in negating H. Very rough, but there are the three possible situations. Now, how to assign probabilities to this DAG, transforming it into a Bayes network? Let's assume that the 3 generalizations we use are deterministic. That is, if H and is true and is true that the witness is accurate, for sure her senses give evidence of H, probability 1. If, again, if she has seen even H, or if she knows even H and it is objective, then then she believes H with probability 1. And if she believes H and is disinterested, for sure it says that H occurred. So all the uncertainty about the answer about the states or the answer of the witness is put on the nodes, on the ancillary nodes H, E, O, V, that can, of course, can have probability less than 1. Problem: what about the case the witness is not accurate, not objective? What we can do? Other are very arguable, highly arguable assumption. I use a sort of kind of default assumption. Let's consider her answer as a random answer. So if H, if she is not accurate with probability 1, that is, it is true that she is not accurate, she can have her senses can have evidence of H with probability 0.5. If it's not objective, she can remember the event with, given that he has seen the event, she can remember the event with probability 0.5. Different situation we will see for the veracious node. This kind of default assumption, random answer, is an hypothesis used many years ago by the Norwegian jurist Per Ekelöf and a Norwegian philosopher Sorel Alden.
They're Swedish.
Huh?
They're Swedish.
Swedish, sorry. Sorry, you see, I'm not a reliable witness. I don't remember well. Yes, and you can find their theories discussed in this book by Peter Jardenfors, Bernd Hansson, and Nils Erik Selin, and the same hypothesis, but in different contexts, and it has been used by Luc Bovens, Fittelson, and Hartmann and Snyder in this paper. So the idea is that the human witness is like a machine. if the machine does not function well, let's assume that we have 50% probability of yes and 50 probability percent no. So the conditional probability table for not S with this default, with the deterministic, with the assumption that allows the common sense generalization is deterministic, and with the default of assumption is this one. The conditional probability for node B is the same, and the conditional probability for the node E is totally deterministic, because we say if the witness is disinterested, she says the truth for sure. If she's interested in saying that H, then she says H for sure, no matters what she believes. And if she is interested in negating H, then she will do that in any case. Very rough assumption. But how robust is this model? I've tried it with a Huygens program with different prior probabilities, and it seems to give reasonable answers with the default assumption. One case that is particularly interesting is, let's assume that the witness is for sure non-accurate and non-objective, but veracious. So let's assume that we know that the witness is non-accurate and non-objective. Then, from an intuitive point of view, what can we do with this witness? It has no value. It's irrelevant if we know for sure that the witness is non-accurate and non-objective, even if she is veracious. But her witness should be irrelevant. And then this is what happens. If we initialize the net with this probability, and then we update with giving probability 1 to the proposition E, what happens is that the prior probability of H, whatever it is, except of course you cannot assign probability 0 or 1, but the prior probability of H, whatever it is in this range between 0 and 1, is left unchanged. So the default assumptions doesn't work badly in this case. It seems that the nets give what seems the reasonable answer. Another interesting case, I applied the net to the infamous blue bus problem. You know, maybe you know it has been discussed at large in the literature. Plaintiff is run down by a blue bus. Plaintiff is prepared to prove that defendant, company Z, operates 80% of all the blue buses in town. And the issue was, can we give a judgment for the plaintiff against the company based on the fact that probability is 80% of given the fact that company Z operates 80% of the blue buses. So we have a probability well higher than the standard of the preponderance of evidence for civil cases. The blue bus cases has been discussed a lot, but I agree with what Lawrence Tribe wrote in his paper, his famous paper, and Lawrence Tribe was not a Bayesian, of course, but I think that he gave the right answers. we might well arrive at a subjective probability of less than 0.5 that defendant bus was really involved in the specific case. And I think that we can give a Bayesian analysis that agrees with Lawrence Tribe's observations. Now, this Bayesian analysis assumes, first, that the statistics can be useful only for assessing prior probabilities. I totally agree with the people that say that naked statistical evidence is not evidence. It can be used only for assessing prior probability. In this case, we have a very simplified case with 1,000 vehicles. And in assessing the prior probability, I think that you have to take into account all the other vehicles circulating in the zone, all kinds of vehicles, not only buses, neither blue buses. Because if we restrict our relevant population to buses, well, this means already taking account of plaintiff witness, because he says that it has been run down by a buses. By a priori, it could be run down by any kind of vehicle in that area. You know, it's quite surprising for me that sometimes in the discussion of the case, this point has not been made. Maybe because you know, you English people are too honest. But in Italy, it will be obvious, taking into account the hypothesis of the guy who is trying to cheat the insurance company. So of course we have to, the relevant population consists of all the vehicles, not only buses. And
they might not have been run down at all.
yeah.
Okay, is this a fact that there was an accident?
And in this case, I say that the real evidence is the plaintiff witness. The fact that the witness says, the plaintiff, that he's being run down by a bus. I remember you that in all the discussion of the case, there are no other witnesses, of course, otherwise it would be simple. There is only the witness of the plaintiff and the naked statistical data. So the evidence, in my opinion, is simply the witness of the plaintiff. Then the solution is straightforward. How credible is the plaintiff? Is the plaintiff? If the probability that he's lying is higher than 7%, the preponderance of evidence standard is not. We don't get the preponderance of evidence standard.
There is also the issue, unstated assumption that all buses are equally likely to run somebody down. Whereas the company that runs red buses, their drivers are dangerous. They ran down this man and said, "Say you were run down by a blue bus."
Okay, this is you get a more complicated version. I didn't try that. Well, you can complicate as you like the case, but given the standard presentation, you apply just Bayesian theorem, and you get that if the probability that the plaintiff is lying is 0.07, then the probability that the bus was a blue bus of the company Z is 4.49%. Well, if we use this prior probability, if we put these prior probabilities in the Bayesian net, we obtain exactly this numerical solution. So of course you can say, so what bother about using Bayesian nets in this case? Of course, in this case it is useless. But it's simply, I give this case simply to check the numerical result obtained by the Bayes net with the default assumption, with the famous default assumption, and comparing it with the straightforward Bayesian solution. They agree. So these are two pieces of evidence for arguing that the net is quite robust, and the default assumptions are not so strange. At least don't give strange answers. Then this the model is very simple, and maybe the only reason to spend time on it is the fact that he gives a general model that can be applied to different real case of witness. So it can be transformed in an object-oriented network class for an analysis of the reliability of human witness. In this case, we have that H is the output node, H star, A, C, O, and V are the input nodes that receives information from outside the class, and S, B, and A are the internal node of the class. There is a problem with this model, I mean a technical problem, is that the input node and the output node coincide in this case, because when you have run the net, you have a new probability for H, and so H is at the same time an input node and the output node. This can be dealt with using a dummy variable in the terminology of information science people, and the dummy variable is exactly H star. So you see, the net is HSBA, the original net, HSBA ACOV, and then we have added another variable node that is H star, which is the input nodes that transmit the new probability value outside when calculation is performed by the net. And the trick is that H star and H have exactly the same value. No, you add a new conditional probability table for node H star in such a way that H star and H have exactly the same probability, the same probability value. It seems that this trick works. I'm not totally sure. A last thing. Okay, I'm not totally sure because I tried the net. I run the net many times, but there can be always some particular value for which something goes wrong. Up to this point, I don't find problems, and of course, I'm not interested in the exact probability value, posterior probability that the system output. I'm interested more in qualitative analysis. Now, changing prior, changing the probability of accuracy, objectivity, and veracity. What happens to the posterior probability? And even this model is not intended for being presented to a court. Possibly yes, but is intended to be used by assessing the case by the expert of the prosecution or defense, or by scientists who love to discuss and analyze legal cases. One extension of the model, someone can say, okay, but what about the witness does not remember, or says, I don't know. No? What about the case of a mafia witness who says, I don't remember, but you were there, I don't remember. It can be dealt with changing the node, the proposition in the node E. For example, you can put that X says that he does not remember H. In this case, you can leave unchanged the conditional probabilities for node S and B, changing only the conditional probabilities for node A, and in this case we can simply switch the 1 and the 0 and left unchanged, you know, oh sorry. We have the conditional probability table for the case witness says that H, and we have the conditional probability table in the case that the witness doesn't say that H occurred, but say, I don't remember. You simply switch 0 and 1. So, this is a very simple model. I showed you all the assumptions that are at the root of this model. Very simple, is a first approximation, but it seems to work well, and in some cases can be useful, I think. Thank you very much for your attention.
We started a little bit late, so we've got time for a few questions.
Thank you for an interesting presentation. So it connects very much to what in argumentation research is called argumentation schemes, where there are these generalizations and they come with critical questions that are kind of sources of exceptions. And you have then modeled the witness testimony as it was studied by Schum. And interestingly, that's more a comment. The PhD student that Henry and I have been supervising has also studied the same example in his dissertation, that is to be defended early 2017, using something like a similar structure. And one of the findings that he has is that this specific argumentation scheme, as we call it, can be modeled as nicely as you do now, because of this, let's say, time series of first thinking about perception, then thinking about memory, and then thinking about whether you are wanting to lie or something like that. Have you also thought of situations where that sequence of sources of exceptions does not exist? Because then the structure changes of your network.
Of course. Not yet. This is a further step. But the point is, I can see easily how to change the structure if you have to figure out a more complex relationship between the basic attributes. Yes, of course, in principle, you can do that. For example, start to put arrows between the ancillary nodes or add some other nodes pointing to the ancillary node. But I think you have a good reason to do that. For example, I think if you want to add a node, for example, going from the accuracy node to the objectivity node, you must have some good reasons to do that, to put that arrow. I mean, I strongly believe, I I said I am a subjectivistic Bayesian, living Bruno De Finetti's school. But I agree that when you give likelihood ratio, you have to justify the probability, like in some way, the probability you give. You know, being a subjective Bayesian, that means to be a wildly rational people that everything works. You know, everything works. For example, in scientific, in calculating bias factoring in physics, you rely on physical laws. So, if you add if I add this arrow, I think we must have some psychological theory which tell us in which way remembering is connected to perceiving. And maybe we can do that, but we have to. But we need a knowledge of psychological and cognitive theory greater than I have, but for sure it is possible. I think that we have to do that. But then, well, the independence hypothesis is very rough. Very simple, but that means that you don't have to tackle this this aspect, to enter more deep in the question of psychological theory of believing and perceiving.
Okay. Actually, sorry, I just want to abuse my privilege. Just a really small, just a clarification thing of the veracity. The way you've got it, you'll say the opposite to what you believe. But sometimes we only say the opposite when it's not favourable to us. Mm. We wouldn't say the opposite if it was favourable to us. And that is more, I think, characteristic of a typical unveracious person. So, and I just don't understand whether your model gets that. Because that suggests that you say the opposite to what you believe. But if your belief is something that's favourable to you, you wouldn't say the opposite. Mm. So if they found out that you weren't there, you wouldn't say you were there. So have I misunderstood your model?
No, of course. Assuming that even the evidence node, what the witness says, assuming that is a Boolean node, is a very yes or not. It's a very simplistic assumption. But in principle, you can extend the node, having a non-Boolean node for what the witness says. This just the conditional probability table get more complicated this way.
We'll come up later. I've got some stuff later on that. Sorry,
this might be partially what you're getting at here. In the case where you've got something special like alibi evidence, isn't that going to be directly conditional on age?
Yeah.
So you've got an.
I was hiding that from my talk. Go on.
Yeah. Alibi evidence. There is a case that I have to study. The alibi evidence. Alibi evidence, yes, I agree that it doesn't fit exactly with this model.
I'll discuss that on Thursday.
Yeah. I want to go back to the Lawrence tribe and the blue bus, because I think there's something there which is very important. No, go back to tribe's statement. No, tribe statement. You notice? You
lost it. Yeah.
Where?
Well,
no. No. Sorry.
In tribe statement, he says, unless there is a satisfactory explanation for the plaintiff not to put more evidence in. Now, one thing Dr. Harding pointed out, there might be accident records from the bus companies. There might also be the bus schedule, because it happened at a time. You would think that he would do that. So there was other, should we say, at least theoretically, readily available evidence. But now, we can change the story. Supposing the blue bus company destroyed its schedules, you know, they took them off the streets, you know. That would be interesting too, right? That would change the whole
Well, in this case, you have to build a complex Bayesian nets, in which the testimony, the testimony net is just a part of it, and you have to add other nodes with this piece of evidence.
And why, you know, the person could have tried, and why they couldn't find it.
Yeah.
Because if there was a good explanation, then he's modifying his conclusion.
Yeah. Sure. But well, but in this case, we change the toys example. We add further complication, and we need a Bayesian network taking account of missing evidence. We have a Bayesian net dealing with the problem of missing evidence, and we have to join the net for the witness with inserting it in the general net, and this is maybe, I don't know, maybe another limitation of the model, because the only point in which you can connect the nets for the testimony with the more general net is the top node H. You know, the event, because information flows only through this through this net. But I think that in principle you can do that. You have H, then the evidence given by the plaintiff testimony, and other arrows pointing to different, starting from H, pointing to other kind of evidence. For example, if H is the case, if it has been really a bus Z, how probable is that the company destroyed the schedule and this kind of thing?
The schedules aren't very reliable anyway.
Still, the point is, what Trav was saying is that the plaintiff didn't try to go on the record.
Yeah. Thanks. Okay, let's thank Paolo.